Assalamu alaikum dear students. In today's digital system design lecture we are going to start from behavior modeling. Learning objectives include explain the significance of structured procedures always and initial in behavior modeling. Now starting from introduction to behavior modeling, Verilog provides designers the ability to describe design functionality in an algorithmic manner. The designer describes the behavior of the circuit, behavior modeling representing the circuit at a very high level of abstraction. The level of abstraction at behavior level is known as high level of abstraction. Design at this level is similar to C programming, with more than it resembles digital circuit design. It means that at behavior level modeling, it is very much similar to C programming. Behavior Verilog constructs are similar to C language constructs. Verilog is rich in behavioral constructs that provide the designer with a great amount of flexibility. Now discuss some levels of abstraction as discussed previously. The low level of subtraction, switch level is the lowest level of abstraction, which is at transistor level modeling. Gate level synthesis tools compile high level code and generate code at gate level. The next level up is the data flow level, the level of abstraction higher than the gate level. Behavior level, it is more complex digital design and it is the highest level of abstraction. Priority is given to the performance and behavior at algorithmic level. Now structured procedures. There are two structured procedure statement in Verilog known as always statement and initial statement. These statements are the two basic statements in behavior modeling. Please note that all other behavioral statements can appear only inside these structured procedure statements. Verilog is a concurrent programming language unlike the C programming language, which is sequential in nature, but Verilog can be modeled as concurrent or parallel form. Activity flows in Verilog run in parallel rather than in sequence. Each always and initial statement represent a separate activity flow in Verilog. Now further details include all statements come in procedure block. Two types of procedure blocks as explained earlier, known as always and initial. Multiple statements per block can be used. Please note some important points that initial blocks execute once at time 0. Always block execute continuously, but it start at time 0 and repeat. But initial block will be executed once and start at t is equal to 0. This figure shows the hierarchy of statements. As you see that initial block will be executed once and here it ends, but always block repeated continuously as per the design. Now further explanation include each activity flow starts at simulation time 0 for both structure procedures, which include always and initial. Statements can't be nested. Please note that nested statements cannot be used in always and initial blocks. Now here detail of initial statement is given. All statements inside an initial statement constitute an initial block. Initial block starts at time 0, executes exactly once during a simulation and then does not execute again. If there are multiple initial blocks, each block starts to execute concurrently at time 0. Each block finishes execution independently of other blocks. Please note that each block finishes execution independently of other blocks. Multiple behavioral statements must be grouped using the keywords begin and end. If there is only one behavioral statement, grouping is not required. This is similar to the begin and end keywords in Pascal programming language or grouping using brackets. In next slide, example is given which illustrate the use of initial statement. In this example, a module is defined known as stimulus. These are the variable types of register type. Here an initial block is given and variable m is used to assign the value 1 bit 0, binary 0. This is single statement and here we have not required the initial begin and end statement. Here you see that multiple statements will be used. This initial block, a statement is given and another statement is given here and begin and end is used. Here another initial block is given and in last block initial is used and $finish is used to finish the simulation and here module is ended. Now here are some explanation is given. 3 initial statements start to execute in parallel at time 0. Here you see that this initial statement, these all will start at time 0. This is also start at time 0 and these 3 initial statements executed in parallel at time 0 and the delay specified. The statement is executed delay time units after the current simulation time. Execution sequence of the statements inside the initial blocks will be as follows. Here you see that at time 0 m variable is assigned the value 1 bit binary 0. Here you see this initial block and here m is given, so no delay is used. Then m will be assigned the value binary 0. Next you see a will be assigned binary 1 at 5 time unit. Let's see from the code. Here you see that 5 delay time unit is used to assign the value to A. This 5 time delay is used, and at 5 time unit A is assigned this value. Next, here you see that #25 is used. It means that 5 time unit time wait for this command, and after that further 25 delay time is used. Ultimately this B is equal to 1 bit binary 0. This command will be executed at 30 time unit. Here you see 5 and this 25, total will be 30 time unit. So B will be assigned the value 0 at 30 time unit. Here you see this 5 and 10 A and X. Let's explain further. This A will be assigned at 5 time unit. This B will be assigned at 30 time unit. And now initial block, this is another initial block. This X will be assigned at 10 time unit because this is the separate initial block, and this Y is assigned the value at 35 time unit. Here you see that 10 time unit delay and further 25 time unit, so total time unit delay will be 35 time unit, and this X will be assigned at 10 time unit, and this Y will be assigned the value 1 at 35 time unit. And here this initial block, this command is executed at 50 time unit. For here you see that this Y will be assigned the value at 35 time unit, B is assigned the value at 30 time unit, and this $finish command will be executed at 50 time units. Next, some further explanation is given. Initial blocks are used for initialization, monitoring, waveforms and other processes that must be executed only once during the entire simulation run. Other alternate shorthand method to initialize values are also used. The use of such shorthand syntax has the same effect as an initial block combined with a variable declaration. Combined variable declaration and initialization. Variable can be initialized when they are declared. Example 7.2 given in next slide shows such a declaration. Here this example related to initial value assignment. The clock variable is defined first. Here this is register data type, and here initial is used to assign the value 0 to the clock. Now instead of above method, clock variable can be initialized at the time of declaration. Please note this is allowed only for variables declared at module level. Here you see that this clock should be defined first at module level, and then this reg keyword is used to assign the value 0. These two statements known as register clock and initial clock are the same as this statement register clock is equal to 0. Now next, combined port data declaration and initialization. The combined port data declaration can also be combined with an initialization. Example given in next slide explains the declaration of this type. Here you see that a module is declared at adder. These are the parameters. Here output reg type is declared, and at the time of declaration it is assigned a value. Here we are initializing 8-bit output variable named as sum with 0. Here we are also declaring the variable C0 as output, and at the same time we have initialized the value 0. Next, another method include for the declaration and initialization known as NCC style port declaration and initialization. In this method, port declaration can be combined with an initialization. Example given in next slide explains this type of declaration. Here you see that in this example, here at the parameter list of the module we have declared the variable sum with register data type, and this is output, and at the same time we have initialized the value 0. Here we have declared port list C0 as output with data type reg register data type and initialize the value 0. Now we are going to discuss always statement. All behavioral statements inside an always statement constitute an always block. The always statement starts at time 0 and executes the statements in the always block continuously in a looping fashion. This statement is used to model a block activity that is repeated continuously. Please note that if the design has the requirement to repeat some statements, then always statement is used in a digital circuit. An example of always statement is including as clock generator module that toggles the clock signal every half cycle. In real circuits, the clock generator is active from time 0 to as long as the circuit is powered on, because in any circuit which include a clock, the requirement of clock is continuously at from time 0 to the end of the simulation or the circuit. Next slide include example which illustrates the method to model a clock generator in Verilog. In this example, a module named as clock generator is defined. These are its parameters including output type, variable is declared as clock, and its data type is reg register data type. Now initial block is used to initialize clock at time 0. Here clock variable is assigned the value 0. Now we have to design this clock which toggle every half cycle, and time period is chosen as 20 time units. Now here always used. This always block is continuous here. Now we have used hash 10, which means that 10 time units delay is used, and after 10 time units value of clock will be assigned with the negation of its value. Here you see that after each 10 time units the value of clock will be inverted. Let's see if clock is equal to 0 initially, then after 10 time units clock will be assigned the value 1, and further 10 time units after as 20 time units total, the clock will be assigned again the value 0. Similarly, at each 10 time unit delay clock value will be inverted. Here this initial block explain that after 1000 time units this simulation will be ended. Now explanation include always statement starts at time 0 and executes the statement every 10 time units. Please note that the initialization of clock has to be done inside a separate initial statement. Here the initialization of clock is in the separate block. This should not be used inside always block because it block repeats again and again, and this initialization is also repeated if this is used in this always block. So initialization will be used in initial block. Here this detail is given that if we put the initialization of clock inside the always block, clock will be initialized every time when the always block is repeated. Further, simulation must be halted inside an initial statement. If there is no stop or finish statement are given to halt the simulation, the clock generator will run forever. Here you see that this $finish statement is given in another initial block, and this always is separate from this statement. Now if we make an analogy between the always block and infinite loop, this is the same, the always block working as the infinite loop working. Hardware designer perspective, it is same as continuously repeated activity in a digital circuit starting from power on. From hardware designer perspective, the always block works as a same as any digital circuit which have the power on. If the power is off, then digital circuit working will be off. So always block has the same phenomena as the digital circuit having power on. Now the activity is stopped only by power off in a digital circuit, and these command $finish or $stop commands are used to stop or finish the always block. Now here some examples are given. This example is related to a multiplexer, 4-to-1 multiplexer. Here a module is defined with the parameter list. These are the input parameters A, B, C and D. and select parameter 2-bit is also input, and out parameter is the output parameter. Here reg out is used because we have required to store the value in the out variable, so this is also declared as reg type. Now here always is used, and if we use this sign, at sign, and this is the sensitivity list which detailed about this always block, that these sensitivity list includes the values that if any of the value is changed from these values, then all of the statements will be executed again and again. Let's see. Always block can be very abstract, similar to C code, and this multiplexer is implemented using if-else statement. Here you see that if select is equal to 0, out will be equal to a variable. If is equal to 1, then it is b. If select is equal to 2, then output will be c, and if select is equal to 3, then output will be d. Now here some explanation is given. This sensitivity list include all the detail and all the variables included in the sensitivity list. If any of the variable is changed, then these all of the always block will be executed. Let's see. If initially a will be 0 and this block will be executed, and after some time a will be 1, then all of the block will be executed again. Similarly, all the entries in the sensitivity list of the always block will be checked at regular intervals, and if any of the variable is changed from these sensitivity list, then always block will be executed. Here you see that if any of these signals change, here the list of signals, then the always block will be executed. Next, please note some methods. Here you see that we have write the sensitivity list using R keyword. Here you see A, R, B, R, C, R, D, R select. This R can be used and can be replaced with this comma. This is same, this working will be same as here ARB or A comma B. CD select. Comma can also be used instead of the R. Now here an important concept is explained, that if any of the parameter is removed from this sensitivity list, then if we remove D variable from this sensitivity list, then always block will not execute if D changes its value, because D is not included in this sensitivity list. So If D value is changed, then this always block will not be executed. Always block will not execute if D changes. If select is equal to 3 and D changes, here you see that D out is assigned to out, D is assigned to out variable, and out will not be updated. This will cause discrepancies between simulated and synthesized hardware. There are no sensitivity lists in real hardware, so it would work correctly as per hardware perspective, but as per simulation perspective, this out is not updated with this value if D is not included here. To avoid the list of all the variables declaration, here if a star is used, it means that all of the signals including in this always block will include in this sensitivity list. It means that if any of the variable changes its values from always block body, then this always block will be executed again and again. This static benefit is that here we have to declare all the variables separately with comma, and if we forgot any variable, then this block will not be executed for the variable which we have forgotten. So if we use this star, then all the parameters will be included in the sensitivity list, and if any of the variable updates its value or changes its value, then this always block will work fine. Thank you. I suggest all the students to these examples. Please practice these examples on the Verilog simulator so that all of the concepts related to always and initial block will be corrected. I hope